Good afternoon, everyone. Let's start the afternoon session. Multi-component wavefield contains different kinds of wave modes. A widely used imaging condition for the multi-component wavefield requires firstly decompose the wavefield into different wave modes, and then combine the different wave modes in the source and the receiver side wavefield to obtain the images. For example, we decompose the wavefield into P waves, P modes, and S modes, and then do the cross correlation to get PP, PS, SP, and SS images. So the PS and SP images are migrated from the converted waves. In the PS and SP images, there always exists a polarity change. Let's look at the example. This is my Lucy. I have one shot indicated by the white dot at the surface of the model, and I have a dense network of receivers also at the bottom, at the surface of the model. So if I construct the source side P mode and the receiver side S mode and do cross correlation, I get a PS image look like this. We zoom into the yellow box to get closer to the image, and we can see that from left to right, the image changed the polarity at some locations. By comparing this image to the true model, we know that those events are true events and from the same reflector, but has different polarity. This is due to the fact that the reflection coefficients change the sign at some incident angles. So that in the isotropic case, it changed the sign at a normal incidence. So in different acquisition with different shot locations, the polarity change at different spatial locations. If we stack the PS images over experiments, it will give us the energy of the true reflectors will cancel each other out. So that will decrease the quality of the stacking image. Today, I will propose a new imaging condition for the converted waves, which corrects for the polarity change automatically. So first, let's take a look at this widely used imaging condition. This imaging condition, we combine the source side P mode and the receiver side S mode to get a PS image, and this similar way to get the SP image. And then we stack the images over experiments to get the stacking image. P and S are decomposed from the wave field. And in the isotropic case, we can use Helmholtz decomposition to decompose to obtain the P mode and S mode. So U here is the displacement vector, and the P is the divergence of the vector U, and S is a curl of vector U. Notice that here P is a scalar while S is a vector. So if the vector U is rotational in the plane, the curl of the U, which is the vector S, is orthogonal to this plane. Let's go back to the imaging condition. So we are doing cross correlation between the scalar and the vector. This gives us a vector. So both PS and SP images are vector images. We call this imaging condition the vector imaging condition. So it's not easy to imagine what a vector image look like. So I will visualize this using this very simple 3D model. This model has two layers. The first layer is in blue. The second layer is in red. I'm showing three planes in the 3D model. The top left panel is a horizontal plane, and the two panels at the bottom are vertical planes which are orthogonal to each other. The yellow dot shows the location of the shot, and I have a 2D network of receivers. The depth is shown as the white line. If I want to compute the PS image, I construct the source side P wave field, and on the top left panel, we observe a uniformly distributed circle. And then we construct the receiver side S wave field. And this is the X component. In the snapshots, we observe a polarity change in the waves. So if we do cross-correlation between the P mode and the X component of the receiver side S mode, we get an image with a polarity change. So in the bottom left panel, there is no energy because this panel is chosen at the location where the polarity changes. This also happens to the Y component. There is a polarity change in the wave field and the polarity change in the Y component of the PS image. So in the Z component, the waves has a more complicated pattern and with a complicated polarity change. This is affected by the reflectivity change the sign in both X and Z, X and Y directions. So we do cross-correlation to the Z components of the receiver wave field and the P source wave field, we get an image look like this. So now we have seen all the three components of the PS image. They all convey the same information of the subsurface, that is the PS reflectivity. But as it is a vector, it adds difficulty to the interpretation. And also we observe the polarity change in the image, so we can't just use those images to stack over experiments. That would decrease the quality of the stacking image. So there have been a lot of procedures proposed to correct for the polarity before we stack the image over experiments. The simplest approach is to assume that the polarity change at zero offset. So we can change the sign of the image where the offset is negative. However, the polarity change indeed happens at zero at normal incident, which is different from zero offset in most cases. So this assumption only holds in the cases with only horizontal reflectors. And more correct methods is to first compute the incident angles, and then change the sign of the image where the incident angle is negative. And there are different methods to compute the incident angles. For example, using the angle gathers by computing the extended imaging conditions. This method is very robust and handles complicated wave fields, for example, the waves interference with each other. But we need to compute spatial lags, and which adds dimensions to the image, so that this method is computationally expensive. Another choice to use pointing vector, but as pointing vector only computes one single value at one spatial point, so it can't handle complicated wave fields. Now we're proposing a new imaging condition which corrects for the polarity automatically. So after we apply this imaging condition, the PS and SP images are ready for stacking. This imaging condition looks more complicated than the former imaging condition. And we call this former imaging condition the vector imaging condition because we get vector images. Now this is the new imaging condition. We call this scalar imaging condition because we are able to get PS and SP scalar images. In addition to use the source and the receiver side wave field, we introduce a new variable that is vector n. N is the normal of the interface, local interface. And I will take the first equation as example to explain the physical meaning behind that. And the more details is included in the CW report. Before I add the explanation, I would like to introduce a cartoon with all the variables I need for the explanation. So the plane at the bottom is the local interface plane, and the vector n is the normal to the local interface plane I. And the propagation direction of the incident P wave is dp, And so vector dp and vector n defines the reflection plane. The reflected S wave is, of course, SV wave is propagating in the plane. So the propagation direction is defined as ds here. And because this is the SB wave, so the displacement is also within displacement u is also within the reflection plane. And the vector S is computed from the curl of vector u, so it's orthogonal to the reflection plane. The bottom the equation at the bottom is the imaging condition for the PS waves. First, we compute the gradient of the incident P wave. This gives us a vector which is parallel to vector dp, and then we do the cross product of the green arrow and vector n, which gives us a vector that's orthogonal to the reflection plane. This is a case where the wave propagates from left to right. In the other case, when the wave propagates from right to left, this green term in this equation gives us also an arrow that is orthogonal to the reflection plane, but is pointing inward. So compared to the other case, the vector is pointing outward. This difference introduces a sign to the imaging condition, which corrects for the polarity change automatically. And here, notice that the green vector is orthogonal to the reflection plane, and the vector S is also orthogonal to the reflection plane, so they are parallel. And now we do dot products between the two vectors and get a scalar image at the reflection point. I apply the scalar imaging condition to the former 3D example, and we get a scalar image. And in this image, there is no polarity change, and this is a scalar image. Compared to the former case, vector imaging condition with polarity change, scalar imaging condition without polarity change. I've shown the equation in 3D, but it also works for 2D cases. So let's go back to the Marmousi, and if we apply a scalar imaging instead and zoom into the yellow box, from left to right, the polarity of the events is not changing, so this image are ready for stacking. Compared to the former case, the vector imaging condition with polarity change, scalar imaging condition without polarity change. Now I'm showing you the imaging condition, and I would like to show an application of the imaging condition to the migration of OBS multiples. OBS stands for ocean bottom seismometers. It contains a hydrophone and a geophone. The hydrophone reports pressure, and the geophone reports three components of the particle velocity. The cartoon shows OBS acquisition. OS here stands for ocean surface. OB here stands for ocean bottom. And the red dot is a source. Blue triangles are receivers. So the wave is propagating in the water layer as pure P waves. When it propagates into the sediments, it transmits into both P and S waves. And when the P and S waves get reflected from the reflector, they're both reflected into P and S waves. In the OBS data, the water layer multiples is quite strong. There have been a lot of approaches proposed to use the receiver side water layer multiples to do migration. This migration will help. The migration offers increased illumination of the subsurface. And this research has been done under acoustic assumption. Now I'm proposing a new method I'm proposing this migration in the elastic sense. So before we use a multiples to do the migration, first we need to separate the multiples from the primaries. So notice that at the receiver locations, the primaries are going up and the multiples are going down. So we can use the up and down separation to separate the multiples from the primaries. And the U here stands for outgoing waves, and down stands for downgoing waves. And the P is the pressure, which is reported by the hydrophone, and the VZ is the vertical component of the particle velocity, which is recorded by the geophone. And alpha is the scale factor, which is related to incident angles and material properties. After separating the downgoing waves, which contains the multiples from the primaries, we're going to use the multiples only for migration. The easiest way to realize the migration is to use mirror imaging. That is, we flip the receivers above the ocean surface and inject the multiples from the mirrored receiver locations. So for RTM, we construct the source wave field and the receiver wave field. This is the ideal case of the receiver wave field. The reason I call it ideal is because when we inject the multiples back, the P waves will transmit into both P and S waves. I marked this. There are some waves I marked out as dashed lines that don't exist in the original wave field, but they will also cross-correlate with the source wave field. Therefore, they will give us artifacts in the image. So this is the common image gathered as a function of shot numbers. So the true events are supposed to be flat because we're using the true model, and all the events with move outs are artifacts. I marked some of the events out with move outs, use yellow arrows. They are caused by the fake wave mounts. So we can simply apply an African filter to filter out, to attenuate those artifacts with move outs and preserve the events, the horizontal events. So to summarize all the procedures that are needed for the elastic migration using OBS multiples, first we separate the multiples from the primaries, and then we use the primaries only for migration using mirror imaging. After applying the imaging condition, we need additional procedure, that is artifact attenuation, to attenuate the artifacts caused by the fake wave modes. Now I'll show you an example, synthetic example. That's the Marmousi, and I modify the Marmousi to increase the water layer such that we can have increased illumination using the multiples to do migration. And the yellow dots at the ocean bottoms are OBS, and I have a dense network of shots at the surface of the model. That's the water surface. So for the following, I will just show you the images below the water layer because we assume there's no reflectors in the water layer. So this is the vector imaging condition, and we cross-correlate the source side P mode and the receiver side S mode to get the image. And because we have many shots, we stack the images over experiments. For comparison, for the fair comparison, I didn't do polarity change to this image before I stacked them. So in this image, in some locations pointed out by the yellow arrows, we can observe that the events are not continuous or weak. If we use a scalar image instead, we can tell that at those locations pointed out by the yellow arrows, the image is more continuous and stronger. So this is a scalar imaging condition, vector imaging condition. We look at CIG at the location indicated by the white line. From left to right, the true events, which are flat, change the polarity. So if we stack the CIG over shots, those energy of the true image will cancel each other out, and we won't get a very good image from this. Instead, if we use a scalar imaging condition, and from left to right, there's no polarity change, and the energy of the true image will be preserved if we stack them over experiments. I've shown you the PS image, Now this is the SP image. This is the SP image using the vector imaging condition. There are also some parts where the image are not continuous. And if we use the scalar imaging condition instead, the image there is more continuous and stronger. So scalar imaging condition, vector imaging condition. Similarly, let me show you a common image gather at this location indicated by the white line. From left to right, there is a polarity change because we're using the vector imaging condition. If we use a scalar imaging condition from left to right, the polarity has been corrected, so we don't need to worry about polarity correction after we get the images. I would like to make some conclusions from the presentation. So in the presentation, I have proposed a new scalar imaging condition for the converted waves in elastic migration. In this new imaging condition, we correct for the polarity change automatically. So after we get the PS images and SP images, they are ready for stacking. And we don't need additional procedures to correct for the polarity. And the only thing we add to this imaging condition is a spatial derivative of the wave field, which is computationally efficient. And I've shown the results. I've demonstrated imaging condition in both 2D and 3D cases. And in my second part of my talk, I show the application of this imaging condition to the OBS, to the elastic migration using the OBS multiples. So we would like to thank Professor Tariq Aklifa from KAUST for his helpful suggestions and comments. Now I'm happy to take questions.